Okay. So, oh yeah, we're going to talk about LNG today. Great. Okay, so just to kind of wrap up from Wednesday, we're talking about blending natural gas with hydrogen as a way of eliminating or alleviating some of the problems with corrosion and in metal pipes and diffusion and leakage in plastic pipes. And so, obviously, this is a way of decarbonizing the use of natural gas. It doesn't completely eliminate it, but it's definitely got some pros, and maybe we'll see more of this in the future. So, okay. So another way that you can move hydrogen around is in liquid form. And so the motivation here is that if you think back in terms of the overall goal of maximizing energy flux, one way to do that is to make the hydrogen denser. So you've got more energy content per unit volume. And the issue with this is that there are really important differences between hydrogen and natural gas in terms of thermodynamic properties that make it a lot more difficult to liquefy. So to liquefy natural gas, we use a process that's called the Linde process. And the basic idea here is if you look on a temperature entropy diagram, you start off over here at your initial point. So this would be like normal temperature and pressure, where you're well within the gas region over here. You go through a compressor where you do isothermal compression. So if you're looking at the cycle, that's where the compressor is over here. And then it goes through a heat exchanger here and undergoes isobaric cooling. So you'd follow one of the isobars down here to some point. And then you go through an expansion valve here, which does isenthalpic expansion, which further cools you down into the liquid vapor region. Then you extract the liquid, and then the gas that's remaining goes through the other side of this heat exchanger where it warms up, and you just continually repeat the process where you're liquefying some fraction of the natural gas and then siphoning off that liquid, and then just keep going through the process. Okay, so a little more detail about that process. So this is what the temperature entropy diagram actually looks like for methane. And it's a little hard to read, so I'm going to outline some important points here. Okay, so these are lines of constant pressure. Those are your isobars. And this one over here, that's 1 atmosphere. And then these blue lines are lines of constant enthalpy. So we were talking about the isenthalpic expansion component here. And that's actually a very important thing in terms of the difference between natural gas and hydrogen. We'll get to that in a minute. And then here's your liquid vapor region down here. Okay, you can see the temperatures you're operating at. The critical point right there is about, so this is temperature in Fahrenheit, so about -120 Fahrenheit. And the pressure is, I don't know, a couple hundred PSI, 200, 250 PSI. Okay, so let's imagine doing the Linde process on this temperature entropy diagram. So here's where we're starting. This is normal temperature and pressure. And the first thing we're going to do is our isothermal compression. So that is just going straight across to the left, constant temperature, but the pressure goes up. So we go up as much as we want to expand it. And then we are going to do isobaric cooling. So we go through the heat exchanger, we follow this isobar down in temperature to however cold we can get it. And once we've done that, then we do the isenthalpic expansion. And what happens during this expansion, there's a phenomenon called Joule-Thomson cooling, which is as the gas expands, it also cools down. And this takes you into the saturated liquid vapor region, basically as far as you can go. And then you separate off the liquid and keep repeating the process. Okay, so one thing that is important in this process is the shape of these lines of constant enthalpy. So you can see that if you start at a high pressure and you follow a line of constant enthalpy down to lower pressure, all of these lines will result in cooling. Okay, so at any pressure above 1 atmosphere, isenthalpic expansion always results in cooling. The other thing is that this is a very simple process. If we go back to the diagram of the process, the only thing that requires an energy input is this single compressor here. And so if you're using some of the natural gas to power that compressor, it only consumes about 10% of the gas that you have. So it's pretty straightforward. Okay, so that's how it works for liquefied natural gas. So let's start out and we'll have a look at the temperature entropy diagram for hydrogen. Okay, it is much taller than the temperature entropy diagram for liquefied natural gas. And that's because the saturated liquid, the liquid vapor region down here is at very, very low temperatures. I can't even read that. The numbers are so small, but yeah, it's like 30, 35 Kelvin. So you're like minus 200 something degrees Celsius. So here's room temperature up here. Okay. And yeah, that's minus 240 degrees Celsius. Yeah, that's the critical point of hydrogen. And that's, compare that to 82 degrees Celsius for natural gas. So it's quite a bit different. There's another key feature here that we have to look at. So these green lines are lines of constant enthalpy, okay? And remember that the isobars they're going to be these red lines here, and they go from high pressure over here on the left to low pressure on the right. So you see that if I'm like up in this region, if I do isenthalpic expansion and I follow one of these lines of constant enthalpy, you're actually going to have heating, okay? You will not get the Joule-Thomson effect. You have to get below what's called the inversion temperature, which is where those lines of constant enthalpy kind of switch their orientation. So natural gas, the inversion temperature is 1,000 Kelvin, so we don't ever have to worry about that. But for hydrogen, it's about 200 Kelvin, so that's minus 73 degrees Celsius. And so that's down right around here. You can see where these lines go from heating to having cooling under certain conditions. And so the reason for this, or the result of this, is that if you're trying to use the same type of Lin process with a single heat exchanger, it's very, very difficult to liquefy hydrogen. And so usually what we do is you'll have another heat exchanger over here, which has liquid nitrogen flowing through the other side of it. And so you will use that liquid nitrogen to pre-cool the hydrogen, and that gets it down below the inversion temperature. The liquid nitrogen has a temperature of 77 Kelvin. So you can get below that inversion temperature and then run it through your second heat exchanger and do the same thing as you do before. So obviously there's another pump over here that requires an energy input. So now you've got 2 pumps and 2 heat exchangers. So things are getting more complicated. There's another problem, and that is that hydrogen actually comes in 2 flavors depending on what the spin of the proton is. Okay, so if you're dealing with 1H, so not deuterium, not tritium, just the most abundant isotope of hydrogen, the intrinsic angular momentum of that proton might be spinning in one direction, or it can spin in the opposite direction. And so if they're both of the hydrogen atoms have the same spin in their proton, we call that orthohydrogen. And if they have opposite spins, we call that para-hydrogen. Okay. And the reason this matters is that there's a different abundance of ortho and para hydrogen depending on what temperature you're at. So at room temperature, it's 25% para and 75% ortho. But to get it to liquefy, it has to be 100% para hydrogen, because that's what's at equilibrium at that temperature. So you need to convert the ortho hydrogen to para hydrogen. And so if you just let this happen naturally as you cool it down, it takes, many, many days for this to happen, and you can lose up to 50% of your hydrogen to evaporation during the process. So that's not good. You can use a catalyst to speed up the process. And so it has to be a paramagnetic material. So these are things like, iron oxide, titanium, activated carbon, that sort of thing. And there's an absorption and dipolar interaction that happens on the surface of that catalyst. So this speeds it up. And then you also have to deal with the heat that is produced by this process. So you've got to have another liquid nitrogen loop in here. So things just get more and more complicated. So you can see that, liquefying hydrogen, it's a much more complex and energy intensive process than liquefying natural gas. And so this is, one of the main reasons that, liquefied hydrogen transport may not be the best way to move hydrogen around. Now, there's, as a result of this, there are different end uses for liquid versus gaseous hydrogen. And there's been some studies that have been done looking at use of hydrogen as a transportation fuel, either as gas or as liquid. Now, this is a study from 1998, so the dollar values are probably a little outdated, but it's useful as a comparative summary. So on the left over here, this is looking at short distance transport. So we're looking at 16-kilometer transport for different types of hydrogen transport. So we're moving the hydrogen 16 kilometers, and we're generating it at a rate of 45 kilograms per hour. So you can see that the different combinations of storage and transport here result in different prices, both in terms of the transport and the storage. So for example, this one right here, this is storing the hydrogen in liquefied form and then moving it by truck. So both of the liquid hydrogen storage options you can see have the highest cost. And again, that's because it's so difficult to liquefy the hydrogen. The lower cost is going to be just storing it underground as a gas, right? And then this MH, this is storing it as a metal hydride, which we'll talk about that in a minute. So the most expensive is actually transporting it by pipeline, and the reason for that is because you have to retrofit your pipelines to be able to carry it. For much longer distance storage, you can actually get away with storing it, much longer distance transportation. You can store it as in liquid form, but it's, and you'll notice that the y-axis in this figure is a lot different from the one over here. If you're transporting it a very long distance by pipeline, the cost goes way up. And again, this is because of the materials you have to use for the pipeline transport. So I guess the upshot here is that for longer distance transportation, actually storing it in liquefied form and then either moving it by rail or by truck turns out to be the cheapest option. Whereas for short distance transport, storing it underground and then transporting it by truck as a gas phase is the cheapest option. So there's all kinds of trade-offs here depending on how fast you're producing the hydrogen and how far you're moving it. Okay. Now this next slide, you can see that we've changed the production rate here from 45 kilograms per hour to 4,500 kilograms per hour. So now we're making the hydrogen very, very fast. And in this case, turns out for short distance transportation, the pipeline just sending off gaseous hydrogen is the cheapest option. Whereas the transporting it by gas and storing it as a metal hydride is the more expensive one. That's for the short distance. And then same thing for long distance. If you're generating it quickly enough, then the pipeline actually becomes the cheapest option. And the reason for this is it's a combination of the greater revenue you get because you're making you're making more hydrogen faster, and the difficulty in liquefying that hydrogen because there's so much of it that you have to deal with that the cost goes way up. So you have to think very carefully about, how fast you're making it, how far you have to transport it, and what's the end use that you're going for. So there's a lot of trade-offs here between liquid and gaseous hydrogen. So, I wouldn't say that liquid hydrogen is a complete waste of time. There are situations where it can be a good thing, but for the most part, it's less useful than some other things. Okay, so rather than turning it into a liquid, what about turning the hydrogen into something that's easier to transport than gas, but easier to deal with than liquid hydrogen? And so some of the other options here include ammonia, these chemicals called metal hydrides, and then liquid organic hydrogen carriers, which are abbreviated LOHCs. Okay, so ammonia is much easier to liquefy. It has a boiling point of minus 33 degrees Celsius. And it's got actually more hydrogen content per unit volume than liquefied hydrogen itself. It's denser. So that's a good thing. You make ammonia by combining hydrogen and nitrogen to make ammonia. This process is called the Haber-Bosch process, and it requires catalysts because nitrogen is very stable. Okay, it's very abundant in the atmosphere, but it's very stable. And so you're going to use a catalyst. They're usually iron-based. You can use other combinations for that. But the basic way it works is that here's the catalyst surface. So you've got your nitrogen molecule and your hydrogen molecules, and they both absorb at different spots on the surface of the catalyst, and they dissociate. And then they kind of wander around, and then they group back together as ammonia, and then they can be desorbed. Now, this has to be done at a very high pressure and high temperature, so it's a bit of an energy-intensive process, but it's fairly straightforward if you have the right catalyst. So now you've got your ammonia, and you're good to go. So like a fertilizer plant, that's what's going on in a fertilizer. They're just making the ammonia. But if you're a hydrogen end user, you need to decompose the ammonia back into nitrogen and hydrogen. And so to do that, you need a different catalyst, which performs the dehydrogenation step here. And these catalysts are a bit more complicated. They have to have three components. Okay, there's an active phase, which provides the sites for the adsorption and desorption. There's a promoter, which is an electron donor, which allows the hydrogen and the nitrogen to split apart. And then there's a support, which is basically just the solid material that the active phase and promoter are attached to. So it gives it high surface area, small particle size, and so you get more adsorption sites. And so there's a variety of different materials that can actually act as the different components of the dehydrogenation catalyst. This also requires heat input, so it takes more energy to decompose the ammonia. Okay, and that I'm going to highlight the third point here, which is that the conversion to ammonia and then the reconversion back to hydrogen, that can use up to 40% of the energy content of the hydrogen. So it's not a very efficient process. There's also the problem that ammonia is highly flammable, and it is incredibly toxic. So you want to think carefully about using ammonia and transporting ammonia. Okay, so that's one possibility. Some people even talk about, I don't remember if I have this later on in the utilization part, but ammonia itself can be used as a fuel, and there are people who talk about using it for shipping. So using ammonia as a fuel for like container ships. Because again, when you burn it, it doesn't produce any CO2, it just produces nitrogen and water. Okay, metal hydrides are another way of doing this, and these are compounds that are metals that the hydrogen actually bonds to, and there's a bunch of them, and lithium, magnesium, sodium, and lanthanum and titanium are kind of the most common metals or metalloids that are involved in metal hydrides. So you can transport the hydrogen as a metal hydride and then take it apart when you get to the place that you're going. It's got the binding step is exothermic, so it releases heat, and then it requires heat input to release it. And typically the way it works here is you will mix the hydrogen and the metal together. The hydrogen will dissolve into the metal and then bind. And this is done at elevated pressure. And most of the binding occurs in this plateau region. And the plateau region occurs at a different temperature for different metals, depending on what you're doing. And then you will discharge at a higher pressure and a higher temperature, again, because of the endothermic nature of these reactions. And so it's important to think about what the temperature is for the plateau region, depending on which metal hydride you're using. So this is, let's see, it's a pressure temperature plot for various metal hydrides. And this is showing you the plateau region for this charging curve here for each one of these. So the pressures are not too terribly high. So 0.1 megapascal, that's roughly 1 atmosphere. And some of these have temperatures that actually work pretty well. So for example, sodium aluminum hydride, you can charge this at 50 degrees Celsius and 1 atmosphere. That's pretty easy, actually. But some of these other ones, like for instance, magnesium iron hydride, you've got to be at like you can do it at relatively low pressures, but the temperatures are very high. So some of these work better than others, but that's generally what we're looking at as far as that charging goes. Okay, so you would charge these things in something similar to what we use to remove CO2 from gas. And the nice thing about this is that you don't need to purify the hydrogen before you run it through these. It'll because they exhibit selective binding, so they'll pull the hydrogen out of whatever gas stream is coming in. They won't pull anything else out. The thing about metal hydrides is that they have a bit of a problem with the transportation side of things. They're pretty good for storage. And the problem with the transportation is that once you get them to the point of use, you take out the hydrogen, and then you're left with the metal that you need to take back to where you started from, right? It's not like with ammonia, you just release the nitrogen. It doesn't matter. It's gone. It's a gas. It's an inert gas. So that's the big problem with metal hydrides. So for transportation, yeah, no, maybe not such a great idea. Much better for storage. Now, the last one of these is what's called liquid organic hydrogen carrier. And these are similar to ammonia in that they can be liquefied and transport a lot more hydrogen per unit volume than you could in the gas phase. But unlike ammonia, these will actually bind with the hydrogen at close to ambient conditions. So you don't have to have any catalysts. Well, actually, you do have to have catalysts, but you don't have to have any crazy pressures or temperatures to get these reactions to happen. The nice thing is that the charging and the discharging can be done at the same temperature. You just have to change the pressure. So it's a kind of pressure swing reaction. And they do require catalysts. So here's a couple of some examples of liquid organic hydrogen carriers. And they're, fairly familiar chemicals. So, benzene and cyclohexane, toluene and methyl cyclohexane. So it's really, a lot of these aromatic compounds can be used for LOHCs. The catalysts, a lot of them use platinum group metals, so those can be expensive, but or nickel or things like that. So now you're dealing with critical minerals. So again, something to think about. There's some drawbacks with LOHCs also, which is that as with the metal hydride case, the carrier then needs to be shipped back from its destination. They're often toxic. I mean, benzene is, obviously carcinogenic. So, a lot of these are kind of nasty things to work with. They're often flammable. And then the other thing is, the ones that I showed you there, those are all aromatic hydrocarbons, right? And so generally these things are made from oil. So that has a carbon footprint now associated with it, both from the production and the refining. And then the last thing is, this issue keeps coming up. Anytime you have to convert hydrogen to something else and then reconvert it back to hydrogen, you're generally going to use about 40% of the energy content of the hydrogen. So it's a fairly inefficient process. So, this is kind of the big problem with hydrogen is storing it and moving it around. And that's a challenge that I think we're going to have to think about. Okay, so that's it for the unit on hydrogen transportation. Any questions about that? Right here.
What's the direct gain on lowering that?
Yeah, okay, so that's a good question. How would you reduce that 40% hydrogen energy content? New materials would be one way of doing it. I mean, if you go back and look at the metal hydrides, some of these operate at lower pressure and temperature than others. So obviously, if you're using this guy over here, magnesium iron hydride, that's going to take a lot more energy than using something like, lanthanum nickel hydride. So there's that to contend with. Something else I want to point out, speaking of carbon footprint, lanthanum and nickel are more difficult to mine than magnesium and iron, right? You can get magnesium from seawater, for example, whereas lanthanum and nickel, there's more carbon emissions associated with that. So there's also that trade-off. Yeah, this works at a lower pressure and temperature, but it uses a material that is more energy intensive to extract. So, there's really no such thing as a free lunch here. All right. Cool. All right. What's up next? Oh, yeah, this is subsurface storage. Okay. So we're switching gears a little bit from transportation to storage. And here's the deal with subsurface storage. Let me come back to this slide in a minute. Why do we need subsurface storage? So because hydrogen has a lower energy density per unit volume than natural gas, it's going to take more of it to get the same energy content as natural gas, right? More volume. And if you think about it, if we just even wanted to replace 1% of global natural gas in 2019, that was 4 trillion cubic meters. That total natural gas. So 1% of 4 trillion cubic meters is 40 billion cubic meters. And that's how much hydrogen we would need. We're going to need somewhere to store that. We can't just be generating billions of cubic meters of hydrogen on demand. And it's just not feasible to store that much hydrogen in surface tanks. The tanks would have to be gigantic. So what we do is we can put it underground because there's a lot of pore volume underground that we can utilize, right? We talked about this in the context of carbon storage. Well, you can also store hydrogen underground. You can store anything underground if you can pump it down. And so the types of formations that are being looked at as storage targets for hydrogen include salt caverns. So this is like the way the Strategic Petroleum Reserve works here in the US, except you would store hydrogen down there. Salt caverns are nice because the salt provides a very, very low permeability barrier that prevents the hydrogen from escaping. So that's pretty cool. Lined rock caverns closer to surface, that's another way of doing that. Depleted oil and gas fields are another potential. These are nice because, as with the case with carbon storage, the fact that these contain oil and gas over geologic time means that they can probably hold hydrogen over geologic time and it won't leak. So that's another thing. And then the other one that's not shown on this diagram, but that a lot of people are looking at is saline aquifers. So same, similar targets to where you would put CO2, but now we're storing hydrogen. Okay. Another reason for doing underground storage is, let's imagine that you're trying to generate clean hydrogen using only renewable resources, okay? I'm not going to tell you what color hydrogen that is. We're color agnostic here. But this would be zero carbon hydrogen. So here's an example. If you're using solar energy. So in Europe, during the summer, they typically have excess solar electricity being generated. And usually what they do is they'll do what's called curtailing. They'll curtail the solar production, which is basically turn some of it off, because there's nowhere for the electrons to go. So one idea would be to take that excess solar generation during the summer and use it to run electrolyzers, store the hydrogen underground, and then in the winter, what you can do is, the sun doesn't shine very much in Europe in the winter, and they need more electricity for space heating. You can use that hydrogen then to run it through fuel cells and generate electricity. So that's one possibility. I'm going to throw out another possibility locally here in Texas. So this is a plot of average wind speed at the Midland Airport over the course of a year. I pulled these numbers from the National Weather Service. So you can see that in the spring, it tends to be very windy in Midland. Funny story, when I lived in Midland, I moved basically straight down there from New Hampshire. And it was a nice day in April. And, in the Northeast on a nice day, you park your car, you go into work, you might crack the windows so it doesn't get too hot inside the car. And I knew it wasn't going to rain because this was Midland in April. And so I cracked my windows a little bit, went into the office. I came back out, the whole interior of the car was covered with dust. So that's because it's so windy out there. It's also very sunny. But I showed you the other day that plot of electricity prices on a windy day in Texas. And one of the key points there was that on a windy, hot day, you typically have high electricity costs in the Houston area and zero, if not negative electricity costs, like in West Texas and the Panhandle, where you're generating wind energy because there's nowhere for it to go. So again, usually they'll just curtail production because there's no place to send their electrons. Well, why not use that to run some electrolyzers, pump that hydrogen underground, and then you can use it some other time when you need it. So, just a thought. Okay. In fact, a lot of people have looked at this. So this is a plot from the Bureau of Economic Geology, and they're just looking at hydrogen resource potential generated from wind. Okay. They're using green hydrogen in the produced from electrolysis with renewable energy sense. Okay. But there's a lot of stuff going on here. But the couple of things I want to point out are, okay, so these dark areas, these are areas that have the highest wind resource capacity. So again, it's West Texas, Panhandle, South Texas. Okay, those are the windy parts of Texas. The other things that they have plotted here are potential transportation pathways and storage pathways. So out here in West Texas, there's a lot of underground gas and other product storage, so you could take advantage of some of that. There's also, all of these upper Permian salts that you could solution mine to make new caverns for storage. Okay, that extends over much of the Panhandle in West Texas. Down here on the Gulf Coast, there's obviously a lot of salt domes. Those are used for, chemical and hydrocarbon storage. But there's also, they've got this contour map here. This is thickness of Miocene sediments, which are, there's a lot of depleted oil and gas fields close to shore here. And those could also be used to store hydrogen. So there's, Texas could potentially be a big hydrogen producer and storer sometime in the future. So that's interesting to think about. Okay, so like we talked about earlier, you can store hydrogen in depleted gas fields, salt caverns, aquifers, or lined caverns or mines. There's all kinds of places you can put it. Okay, as with anything that we talk about in this class, there's challenges associated with subsurface storage, some of which, or much of which, has to do with the different properties that hydrogen has compared to other gases. Okay, so this is looking at the density of different gases as a function of temperature at 20 megapascals. So that's roughly the pressure at 2 kilometers depth under hydrostatic conditions. So CO2, the density is hundreds of kilograms per cubic meter. Methane, it's on the order of 100 kilograms per cubic meter. Hydrogen is much, much lower. It's between 10 and 15 kilograms per cubic meter. So it's much, much less dense than other gases. The other thing is, remember back to our capillary pressure stuff that we did with CO2. It's got where is it? This is hydrogen over here. It's got a higher interfacial tension with water than other hydrocarbons. And so that means it's going to exist at a higher capillary pressure when it's in the pore space. And it's also much less viscous than other gases. So you can see it's down here around 1 times 10 to the minus 5 Pascal seconds. So half to, about half as viscous as methane. It also has a higher diffusion coefficient because it's a smaller molecule. And so this means that it's a really kind of slippery, hard to contain gas. Okay, it's going to migrate by buoyancy much faster. It's going to exist at a higher capillary pressure. The lower viscosity means that it flows more easily under an induced pressure gradient, and it will diffuse away more rapidly. So it can be a lot harder to contain. So going back to whether you can use this actually in depleted oil and gas reservoirs, given that they've contained oil and gas. It's not directly a one-to-one comparison the way it is more or less with CO2. Okay, so I'm gonna leave it at that for today. Remember, we will not have class on Monday, so I will see you all back here next Wednesday.